Hello, everyone. Good morning, good afternoon, or good evening, depending on your time zone. I'm Pascoal Palhuza, faculty member and currently director of the Physics Institute at Campinas State University in Brazil. He also co-chair of the SCES 2020 conference. As you know, SCES 2020 conference was postponed to next year due to the COVID-19 pandemic, and the SCES webinar series is organized to keep your community connected and live during the absence of the in-person SCES conference. So I'd like to welcome all of you to today's SCES webinar. Thank you very much for joining us for this event, and I hope you and your family are well and healthy during this difficult time. Today, the participants are welcome to ask questions after the talks. The participants in the Zoom meeting can ask questions using the raise hand feature, which can be found by clicking on the participants in the menu at the bottom of their screen, then clicking on the small blue hand at the bottom of the participant list box, while participants in the Facebook can use the chat to ask questions. During the presentation, please keep your microphones muted and your videos off, but you are welcome to start your videos and unmute your microphones to ask questions. So to introduce our speaker for today, I'd like to invite Professor Múcio Continentino from the Brazilian Center for Research on Physics in Rio de Janeiro, Brazil. Professor Múcio is a very active member of the SCES community. He was a co-chair of the memorable SCES 28 in Búzios, Brazil, and he's a member of the International Advisory Committee for the SCES 2020. Professor Múcio, thank you very much for being with us today, and you may begin the introduction. The Zoom floor is yours, please.
Thank you, Pascoal. Good morning, good evening to everybody. So this morning, evening, we have two speakers. It's my pleasure to introduce them. I will introduce both so they can go directly after the first finishes. And so our first speaker is Dr. Aline Ramires. I have the pleasure to introduce this particularly because she was my MSc student at CBPF in Rio de Janeiro. Already at that time, it was seen that she would be a very successful scientist. Then Aline came to the United States to work with Piers Coleman, where she did her PhD with him, and then continued, moved to Switzerland, where she worked with Manfred Sigrist in all the way through this career her career in strongly correlated system. And now Aline is in the Paul Scherrer Institute in Switzerland. Next, our speaker is Dr. Yasuhiro Tada from the ISSP. He finished his PhD in 2010 at Kyoto University, working with Professor Norio Kawakami and Professor Satoshi Fujimoto. So it's really a pleasure to welcome these two young researchers, and I'll give the words to Aline, that is going to speak about stabilizing even-parity chiral superconductivity in strontium ruthenate. Welcome, Aline.
Thank you, Múcio, for the introduction. Thank you, Pascoal, for the invitation to participate on this webinar series for SCES. And today I'm going to tell you about a story that we have been building up over the last years. As you can see, we have a few references here on the right bottom corner on our attempts to understand the superconducting state of the material strontium ruthenate. In particular, today I'll tell you the story of how we found a way to stabilize the chiral even-parity superconducting phase in this material. So I'd like to start acknowledging the multiple sources of funding I had over the last years from Brazil, from Dresden, and from Switzerland, and also my collaborators. This story started after my interactions with Manfred Sigrist at ETH in Zurich, but the work I'll be focusing on today was a collaboration between Daniel Achterberg, Philip Bryden, and Karsten Tin, and Han and Henry, the respective students, each one of them in a different corner of the globe. So let me start with the outline of the talk. I'd like to start giving a brief review of the experimental results, in particular highlighting how the new NMR experiments impose important constraints on the nature of the order parameter for this material. Then from these new constraints, we are going to ask the question of what's the most likely order parameter. And I'd like to propose here that chiral D wave is a good candidate. With this proposal, we see that we need to construct a more complete model for this material, which not only has 3 orbitals, but it's also constructed in 3 dimensions. And from a simple proposal of local interactions, we can see that in the limit of enhanced Hans coupling, we can stabilize the chiral D wave with one key ingredient, which I'll show is the momentum-dependent spin-orbit coupling between layers, which has usually been neglected given the 2-dimensional character of this material. And then I conclude with outlook of ongoing and future work. So perhaps the early experiment that suggested that this superconducting state is of a chiral P wave nature in this material was the night shift, which showed no change for the spin susceptibility as one goes below the critical temperature, marked here around 1 Kelvin. This suggested a triplet superconducting state with a D vector along the Z direction, in contrast to this line, which is the expectation of a singlet state. Furthermore, muon spin relaxation experiments and polar Kerr effect also indicate evidence for onset of time reversal symmetry breaking at the critical temperature. So these experiments taken all together, they look like enough evidence for a chiral superconducting state. But from the beginning, there were already some contradictions. For example, the behavior of the specific heat as a function of temperature seemed to follow temperature dependence that indicated the presence of line nodes, in contrast with an isotropic graph that would be expected for a chiral P wave state. Line nodes are also inferred from other experiments, such as thermal conductivity, penetration depth, and quasi-particle interference more recently. Another experiment that contradicted the chiral P wave proposal was the behavior of the suppression of the of the superconducting state for in-plane fields. So for low temperatures, one would see that the transition from the superconducting to the normal state would become first order, which is reminiscent of the idea of a Pauli limiting effect, which would not be possible or would be in contradiction to the early night shift experiments for a magnetic field in plane and a D vector along the Z direction. So earlier last year, we became aware of new experiments, new NMR experiments that brought up the issue of heating in this kind of experiment and showed that more careful investigation displays, in fact, a reduction of the spin susceptibility below TC. And I believe this is strong evidence for superconducting state, which is not the standard chiral P wave, but it could be still a singlet or a triplet state with an in-plane D vector. So one could make a bookkeeping of different experiments, what is observed and what are their evidence of. And in particular, the chiral P wave, it satisfies 2 important constraints, namely the 2-component nature of the order parameter, which allows for a time reversal symmetry breaking order parameter, but it's in contradiction with other robust signatures, such as the presence of line nodes and the NMR night shift response. So if one look at references of reveals in the field, one would find this kind of tables that list all possible superconducting states according to the point group symmetry of this material. And in principle, one would see that the only two-component order parameter that we would have available would be this in the EU channel that gives rise to this chiral kx plus or minus iky state. But this table has a hidden assumption, which is it assumes the material is purely two-dimensional, which is in fact observed by experiments such as quantum oscillations, which show here a cylindrical Fermi surface with a corrugation which is already enhanced by a factor of 15. But if one looks at the complete table concerning the different irreducible representations of T4H, one sees that a two-component order parameter is not only possible for this kind of chiral P wave, but it's also possible for a chiral D wave in even-parity EREP, but also there's the possibility of having a chiral P wave prime with a D vector in plane, where the two-component property here of the order parameter is carried by the spin-oriented spin configuration of the pair. Now, why we have not thought about this order parameter seriously before? Well, they both carry line nodes along the plane at kz equals to 0, which sounds very unlikely for a material which is strongly two-dimensional. But even though it's hard to imagine a mechanism for this superconducting states, in particular, a D-wave superconductor seems to satisfy all this phenomenology that can be inferred from experiments. So we decided to spend a little some time investigating how one could stabilize this kind of state in this material. So to that, I'd like to start focusing on the normal state and sharing with you some data that was made available almost a decade ago now, which is this LDA type of calculations on top performed without spin-orbit coupling and on the bottom with spin-orbit coupling. So one can see here that in absence of spin-orbit coupling, the bands do have a dispersion along the z-axis and would even cross each other as one goes along the z-axis in the Brillouin zone. Once a spin-orbit coupling is turned on, these crossings, they become avoided crossings, and the bands look much more flat than they actually are in terms of, if one thinks in terms of hopping amplitudes. So the message here is that spin-orbit coupling reduces the modulation along the z direction of the Fermi surface and makes Sr2RuO4 look much more two-dimensional than it actually is. Furthermore, spin-resolved ARPAS experiments can track the orbital and spin configuration along the different Fermi surfaces. And here, for example, it becomes clear that the winding of the orbital content as you go around the Fermi surface for the plane kz equals to 0 is qualitatively different from the winding at a finite kz. So the question now, what are the consequences for pairing of this non-trivial texture of orbital and spin degrees of freedom along a three-dimensional Fermi surface? So we go back to microscopics. And for Sr2RuO4, it's well established that the main degrees of freedom are electronic degrees of freedom are the 4d electrons coming from the ruthenium ions. These ruthenium ions are in an octahedral environment formed by the oxygens, which splits the manifold into Eg and T2G, with the T2G being the lowest lying manifold. And if we think about this problem as it was originally taught in two dimensions, we put these orbitals on a square lattice, and what we get is this Hamiltonian that might be familiar to some of you, which is written in the orbital basis, where here is made explicit the orbital and the spin content. In this matrix form, we have in black intra-orbital hopping, in red inter-orbital hopping, and in blue spin-orbit coupling. But this is not the most general model one can construct. And to construct the most general symmetry allowed Hamiltonian, we propose a different parameterization in terms of this AJB functions of momenta and matrix and a product of Gell-Mann matrices, which are 3x3 matrices, which will keep track of the orbital content, and Pauli matrices, which will keep track of the spin degree of freedom. So in total, there are 9 times 4, 36 of these functions, which sounds like a lot, but in presence of inversion and time reversal symmetry, we have a restriction to only 15 of these functions, which are symmetry allowed. So this is in contrast to only 6 functions that are used to parameterize the 2-dimensional model. So in 3 dimensions, there are 9 extra terms to the Hamiltonian that were not taken into account before. So this table summarizes essentially everything that is possible for the normal state of Strontium ruthenate within the T2G manifold. So the A's and B's here are the symmetry allowed terms that come here with different functions, with a momentum dependence that is led by the irreducible representation associated with each of these terms. And here we also summarize what's the physical process associated with each of them. So in gray, you see intra-orbital hopping. In red, you see interorbital hopping. In blue, the atomic spin-orbit coupling. And in green, the momentum-dependent spin-orbit coupling terms, which here are all even in K, but we were usually neglected. And here we highlight that these last 3 terms, they are strictly only present in a 3-dimensional model. So that much about the normal state. About the superconducting state, we would like now to propose a similar parameterization. So we are used to think about the order parameter in the single band scenario and associating a D vector with different spin configuration of the pair. But what we would like to propose now in this 3-band, 3-orbital scenario is some kind of D tensor with 2 indexes, where the orbital content of the pair is also made explicit. Again, there are 36 such functions, which can be divided in even and odd parity by a combination of fermionic antisymmetry and the presence of inversion symmetry. So now, if we focus on this 15 set of matrices that will be associated with even parity gap function, we can enumerate them, organize them here in this table. Again, we can go over the exercise of associating them with different irreducible representations of the point group. And now we can explicitly also make a comment about the orbital content, if it's symmetric or antisymmetric in orbitals, and the spin content, if it's a singlet or a triplet. So one interesting thing to note here is that now, since we are able to antisymmetrize this pair amplitude in the orbital degree of freedom, we are able to construct S-wave triplet states, for example. So focusing again, or still in this even parity scenario, we propose a local interacting Hamiltonian of the Hubbard-Kanamori type, including intra-orbital interaction, inter-orbital interaction, and Hans coupling J. And we go over the exercise now of decomposing this interaction in different irreducible representation channels, in the different symmetry channels. And we find different combinations of U's and J's for each case. In particular, something interesting happens for the ones that are highlighted here in green. That is, if Hans coupling becomes the dominant interaction in an effective model, these channels, they become naturally attractive. So what we do, we essentially minimize the free energy of this complete 3-dimensional normal state in each of the symmetry channels to investigate which is the superconducting state, or which is the symmetry of the superconducting state that would be established. So we parameterize our Fermi surface according to the best fit we can make to DFT calculations. And the best fit gives a Fermi surface, which is the one shown in Bordeaux color here. And the Fermi surface is thick because it's a projection at the kz=0 plane. So the width represents the wiggles it has along the z-axis. And for this set of parameters that reproduce the Bordeaux Fermi surface, we find a spin-orbit coupling of around 60 MeV, and this new type of spin-orbit coupling that is momentum dependent of the order of 10 MeV. And if we minimize the energy, what we find is that the state that wins is in the A1G channel, so a rather trivial superconductor. But not far from there, we can find an EG solution. And the point here with atomic spin-orbit coupling a bit smaller and this momentum-dependent spin-orbit coupling slightly bigger gives rise to the blue Fermi surface, which is still in good qualitative and even quantitative good agreement with theoretical calculations and experiments, but allows us to stabilize a rather non-trivial even-parity state. The lines here, they give some quantitative estimates of how close these new Fermi surfaces would be from the optimal one, or the one that matches better previous DFT calculations. So the message here is that, yes, it is possible to stabilize a chiral EG order parameter in this material. And in particular, something interesting happens when we plot the gap amplitude on the Fermi surfaces. So we find here that the gap amplitude is more or less the same at the beta and gamma bands, which does not make us able to divide the problem in the gamma band or in the alpha beta bands as it was proposed before. And in particular, the gap is dominated by an order parameter that has this character 5363 in terms of this Gell-Mann times polymatrices, where the 5 and 6 here are explicitly written. They are antisymmetric, meaning that the pair amplitude now is antisymmetric in orbital content and has a triplet character for the spin degree of freedom. And interestingly enough, the two-component nature of this order parameter is now carried by the orbital configuration. So in the orbital basis, this would be an S-wave spin-triplet orbital antisymmetric order parameter. But once we fold it and project it into the band basis, we find a D-wave pseudospin singlet state. So with that, I would like to conclude, emphasizing that the nature of the order parameter in Stronk's ruthenate is still under debate, even more now in light of new experiments that started to be available last year. I would say that it's well established that it's not the standard chiral P wave state. And to my understanding, one of the best candidates is a chiral D wave state. This state has been dismissed based on the strong two-dimensional character of the Fermi surface of this material, but we could show that that a local mechanism was able to stabilize this state in presence of this new type of spin-orbit coupling that has a momentum dependence along the z direction, which has been usually neglected. And you might be wondering, how did we find out that we should look at this specific direction in this big parameter space that we have now with this Hamiltonian, which has more than 20 parameters? For that, we used the concept of superconducting fitness, something that I don't have the time to share with you here in detail, but we discussed in the supplementary material of this recent publication, that provide us a very computationally cheap guide to sample parameter space, and instead of doing that numerically. And of course, this is not the end of the story. This proposal leaves us with questions. In particular, are there unique signatures of this chiral D wave state that would distinguish it from other chiral states? One interesting aspect is the presence of probability Fermi surfaces, which are guaranteed to be there in case of an even-parity time reversal symmetry breaking superconductor. And this structure might have implications for responses at very low temperatures. Furthermore, there is interesting behavior of the critical temperature as a function of strain. In particular, we have preliminary data that shows that the TC under strain along the Z direction is suppressed, even though the density of states is enhanced in this process, something that sounds a bit contradicting and seems to be unique to this inter-orbital kind of pairing that we propose. So with that, I stop, and I would like to thank you all for your attention.
Okay. Thank you, Aline, very much for this very nice talk. And now the session is open to questions. So I was supposed to see some blue here.
There is one question there.
Okay, so can you make a question, please? Because yes.
May I speak? I'm Yoshima Eno.
Sure. Yep.
Yes. Thank you, Aline, for a very clear talk. Thank you very much. Your proposed state is 5-3 and 6-3. So
Yes.
they are spin-triplet, right?
In this microscopic basis, yes.
Correct. So are they compatible with the NMR night shift experiment if it turned out to be spin singlet?
Yes, thank you for the question. That allows me to clarify something. And yes, that's a very good question, and goes into the discussion of in which basis are we talking about this order parameter. Of course, in this what I call microscopic or orbital basis, it seems to be a spin triplet, but once projected into the band basis, it's a pseudo spin singlet, as it should be to be in accordance with the even parity EREP. So here it means that some part of the susceptibility response would also be stemming from the orbital content, not purely from the spin. So the response we would expect for a night shift would be essentially the same as for a plain vanilla singlet state. So it is in accordance with the recent NMR.
Okay, thank you.
Other questions? So if there are no questions, I would like to make one. Aline, what is so typical of this material that has this, so this type of approach could be useful for other systems also, or what makes this material unique to present that kind of?
Yes, I think the main feature that allows us to propose this kind of construction is the multiple internal degrees of freedom. So here it manifests itself as the orbital content. So we have this T2G manifold with 3 orbitals. But in other materials such as iron selenides, for example, we have a similar scenario, and similar proposals were made, for example, for potassium iron 2 arsenic 2 recently. One could think about an internal degree of freedom related to a sublattice structure, and one could make a similar construction. So this is I think it's a valid perspective, or I would say an important perspective for more complex scenarios or multi-band, multi-orbital, multi-degree of freedom problems.
Okay, thank you very much. So there is a question here by Dr. Nimrod Bashar.
Hello, yes. Aline, thank you for a very nice talk.
Thank
I really enjoyed it. I just have a question. Can you, for example, from your model, get some information about the Fermi liquid response, for example, in strontium ruthenate? As a function of strength, for example, or can you see something about the optical conductivity that we can measure, for example?
In principle, yes. So one could ask the question, what this construction with a more complete normal state, how does the responses on the normal state would change? In principle, one could use this parameterization as a starting point. Here we are focusing more on the superconducting properties, but would be worthy perhaps investigating if there is some signature in the normal state that allows us to infer, for example, what's the magnitude of these terms that are usually neglected? What are the amplitudes here?
Okay, thank you.
Okay, so if there are no more questions, I would like to invite Dr. Yasuhiro Tada, that is going to speak about quantum criticality of magnetic field induced order in a correlated Dirac semimetal. Thank you, Aline. So welcome, Dr. Tada, please, you can start your.
So can you see? Maybe, can you hear me?
Yes, we can.
Yes.
Okay, good. So thank you very much for for this seminar. I would like to thank all the organizers and also all the participants from the different regions of the world and from different times. So today I'm going to talk about this, some kind of quantum criticality physics. And because our today's main target is our quantum criticality, let us begin with a general good. General introduction to quantum criticality. So quantum criticality, as you know, are critical phenomena driven by quantum fluctuations, which is clearly distinguished from summary fluctuation physics. And here is the, okay, good. Our typical phase diagram are in the interaction and temperature plane. And interaction could be sometimes tuned by pressure, and by applying pressure, the transition temperature is reduced, and eventually it becomes zero if this quantum critical point is this around this quantum critical point. You may have strong quantum fluctuations, and this effect can be observed in some cases even at finite temperatures. That is very interesting. And this characteristic phase diagram can be observed in various materials like these materials. And the concept of quantum criticality itself is very kind of a general one, and can be applied even to insulating system. But people are more and more interested in metallic systems. There is quantum criticality in metals. In conventional insulators, you only have critical bosons. And for example, in ferroelectric system or insulating magnets, you have charge degrees freedom or spin degrees freedom only, which are the critical bosons. They are critical bosons. And in addition to that, in metals, you have gapless fermions around the Fermi surface. In full metallic system, the Fermi surface is two-dimensional, so you have a lot of fermionic excitations around this Fermi surface. So theoretically, it is rather hard to treat such a system. But in semi-metal, with point node-like Fermi surface, this is just a point whose dimension is just zero, so we have less fermionic excitations. So theoretically, it is rather relatively easy to understand. So from experimentally, they have emerged several good candidates for correlated Dirac or Y symmetries recently. Of course, graphene is most famous one, but this is rather weakly interacting. But people found that, for example, in perovskite oxide, molecular crystal, or some selenium-based materials or cold atoms, people expect that strongly correlated Dirac electrons are realized in these systems. So it's interesting to study quantum criticality in Dirac symmetries. And theoretically, such a problem has been investigated in detail already. This is one famous study by Igor Helmut in 2009. And he did RG, renormalization group calculation for kind of effective model where we have this Dirac electron part and a bosonic excitation part corresponding to, for example, magnetic order, and a coupling between these fermions and bosons. The coupling has this coupling constant G square. And in this RG phase diagram, what is interesting is that this fixed point F, at this fixed point, this coupling G square is not zero. So therefore, at this fixed point, fermions and bosons are strongly coupled. And this fixed point describes the quantum criticality in correlated Dirac electron systems. And there are already many theoretical studies, including field theories and numerical simulations. And thanks to them, quantum criticality of correlated Dirac systems has been well established already. So far so good. So given this background, now my question is, let's apply a uniform magnetic field into such a correlated system. So the reason why I'm interested in a magnetic field is that a magnetic field in correlated Dirac systems has a very strong influence. Suppose we have, one of the famous phenomena is the so-called magnetic catalysis. So let me explain this. Suppose we have two-dimensional Dirac cone like this, and this is strongly correlated. So I have some interaction G, and when interaction is strong enough, I have some symmetry breaking like magnetic order, and I have some order parameter M, which grows when the interaction is above G critical like this. So now we introduce a uniform magnetic field into this system. Then my Dirac cone is discretized into lambda levels. The point is that I have a zeroth lambda level, and therefore we can have finite digital states at zero energy. This can amplify correlation effects. Therefore, we can have an enhanced magnet order parameter M compared to the non-zero magnetic field case. So this is the basic physics of magnetic catalysis. And this is a real typical calculation of magnetic catalysis in a simple kind of a toy model in so-called large M limit corresponding to mean field level approximation. So this G is interaction strength, and Mj is a kind of an order parameter like magnetization. And you see that when the interaction G is small enough, if you apply magnetic field, then your order parameter grows linearly in B, and it's non-zero as long for any non-zero interaction G. It's really catalyzed by magnetic field. On the other hand, when the interaction is strong enough, order parameter is basically constant plus B square when the magnetic field is small enough. And finally, what is most interesting is the physics around this quantum critical point. Then my order parameter is basically square root of B with some universal prefactor 0.4 446 in this case. So this is typical calculation result using kind of mean field-like approximation. And there are already a lot of theoretical calculations for magnetic catalysis. However, as far as I know, the true critical behavior of magnetic catalysis beyond mean field level approximation has not been known. And more concretely, I'm interested in how this order parameter at quantum critical point behaves as a function of magnetic field. So this is my question. So in order to study this problem, I would like to introduce a very simple toy model, so-called pi-Firac scale lattice model, spinless Dirac fermions on pi-Firac scale lattice. So this is a very simple model, one realization of Dirac fermions in condensed matter physics, but I'm interested in this universal nature of criticality. So if I can say something from this model, maybe the result can be applied to other similar models as well. So my Hamiltonian is very simple. I have this kinetic term, and I have this magnetic field, and I have this interaction term, which is just nearest neighbor repulsive interaction. So this model is very simple and has been analyzed in detail by quantum Monte Carlo, but without magnetic field. In absence magnetic field, people have established this kind of phase diagram. So you see that by increasing interaction V, then you find a CDW phase transition at some quantum critical, with some quantum critical point. So my question is, what happens if I add magnetic field in this phase diagram, especially around this quantum critical point? In order to study, analyze this model, for several reasons, I used infinite DMRG. So infinite DMRG has two important points. The first thing is that we have numerical control parameter, so-called bond dimension chi, which should be taken to be a kind of large integer. And second is that my system is quite anisotropic. For x direction, it's infinite, but for y direction, it's very small, less than, let's say, 10 sides or 20, at most 20 sides, I would say. But point is that if I have some kind of characteristic length scale, which is shorter than system size, then the system could be regarded as a two-dimensional system. So this is the basic philosophy of DMRG when we apply DMRG to two-dimensional system. So in my particular case, I did careful extrapolation of this bond dimension to infinity. This can be this is possible because our system is kind of weakly gapped. And second is that we did a careful analysis for the system size dependence, and where we find that my characteristic length scale is magnetic length. Because of this magnetic length, we have some weak gap. Therefore, by using DMRG, we can successfully describe nearly gapless but weakly gapped 2D system. That I will explain in the following. Okay, let us first discuss magnetic catalysis when the system is away from quantum critical point. So the left panel shows the order parameter, CDW order parameter, as a function of magnetic field when the interaction is small enough, and the right panel shows the CDW order parameter when that interaction is large enough. When the interaction is small enough, we see that my order parameter is basically linear in B, while it is constant plus B squared when the interaction is strong enough. So these are basically consistent with the known large N field theory results. That's fine. So these are just benchmark calculations. So by the way, for comparison, we included numerical mean field calculation results with these red symbols. So numerical point is that we computed the same quantity M for two different system sizes, Ly equals 6 and 10 with different symbols. And we see that these two symbols just coincide when the magnetic field is finite, non-zero. So this means that at least in this parameter regime, magnetic field is kind of shorter than the system size. Therefore, we don't have a severe finite size effect. And we are basically looking at results at thermodynamic limit. Okay, so far so good. So let's go to the magnetic catalysis at quantum critical point. So red panel is a linear plot, linear scale plot, and light panel is a log-log plot. So for the smallest values of magnetic field, we have some deviations between the different system sizes. This is because in this region, magnetic length is so large, therefore, and the quantum fluctuation is so large, therefore we have some finite size effect. But for larger magnetic field regions, we don't have such finite size effect. Therefore, we can safely discuss kind of a thermodynamic limit results only focusing on these regions. And we do our power law fitting of the numerical data and obtain the result that my order parameter shows anomalous power law behavior with this funny critical exponent, 0.355, which is clearly different from the mean field result, square root of B. So these are just numerical results. Now we want to try to interpret this numerical number based on some physical argument. So here we introduce scaling ansatz. And the point is that in my scaling ansatz, I included magnetic length as a scaling parameter. So this is seemingly similar to the conventional finite size scaling, where we have the system size as a scaling parameter, but these two scaling ansatz are kind of different, seemingly similar but different. And following, based on my scaling ansatz, I can easily show that at quantum critical point, my order parameter is basically given by this. So this means that the funny number 0.355 is nothing but this critical exponent ratio of critical exponent beta divided by beta over 2 nu. So this is a physical interpretation based on this scaling ansatz. And this scaling ansatz can be confirmed by dead graphs. And we can perform this nice dead graphs. And we don't have a finite size effect because two system size results just coincide. And from this data graphs, we can evaluate these critical exponents, and now we can compare these obtained results with the known results. As I said previously, the model has been analyzed in detail when there is no magnetic field, and the critical exponents have been obtained like this. And but my results is obtained from this LB, magnetic length scaling, and methods are quite different, but we obtained basically the consistent same result. So this can be rather easily understood when once one realizes this three-dimensional phase diagram. Okay, people have been interested in this temperature interaction plane where you have this quantum critical point, but I have discussed this magnetic field interaction plane, but we are looking at the same quantum critical point of course, all the quantum critical phenomena around this quantum critical point in this three-dimensional space should be characterized by the same set of critical exponents. Therefore, we obtain the same consistent result with the previous results. And by in analogy to this temperature interaction plane, we can now draw this phase diagram in magnetic field and interaction plane. Similar to this familiar case, we have quantum critical region in this red shaded region where we can expect anomalous behaviors in physical quantities. So this is the main result. And in the last 1 or 10 minutes, let us discuss some other analogies between our system and known other systems. So here I want to focus on ground state energy density itself. I would here point out, would like to point out that the magnetic field dependence of the ground state energy density can be regarded as a kind of magnetic analog of Kashmir energy, and it potentially may contain some kind of universal information of the field theory at the critical point. So this is, we have some reasons for this expectation, because it's well known that in 1+1 dimensional system, quantum criticality is described by a kind of a CFT, conformal field theory, and where we have this Kashmir energy for the conventional system size dependence, and this Kashmir energy contains some kind of universal information of the theory like central charge, and people are now trying to generalize this idea to higher dimensional systems. So we have some kind of analogy, we expect some kind of analogy between these two. Therefore, we expect this singular term may contain some kind of universal information. And what is more interesting is that this kind of singular magnetic Kashmir energy could be, in principle, experimentally observed via diamagnetism, which leads to universal scaling of orbital magnetic moment. And again, we can find some kind of analogy to a known interesting system. In this case, critical Kashmir force observed, for example, in helium-4 thin film, where people observe this nice scaling behavior of Kashmir force. So I would expect it is an interesting future direction to experimentally study and try to find some kind of universal critical nature of Dirac, correlated Dirac electron systems under magnetic field. So that's why, thank you very much.
Thank you very much, Dr. Tada, for this nice talk. And we are open now to questions. So
may I?
Yes, Aline, go ahead, please.
Hi, Yasuhiro. Thank you for the nice talk. I have maybe a naive question. So when you showed us the ends, the scaling ansatz you use, you write it in terms of H, the conjugate field, but also in terms of the magnetic length. So is this for convenience, or because is it somewhat redundant because the field is already inside the magnetic length? Do you see what I mean?
So this H field is not magnetic field. This is just a source field. In theory, you just introduce source field, which couples to our order parameter. This is just a theoretical tool. It's not a magnetic field.
So it's not necessarily so we're not talking about the magnetization, therefore it's not the same.
This H is just artificial, some kind of theoretical tool, and this G and H are just common. I didn't include here, but this G and H are quite common scaling parameters.
I see.
Common also for this conventional case.
Okay, thank you.
Let me see here if I have more hands. Are there any more questions? Please unmute the microphone because I cannot see here the list of hands.
Mhm.
There is one question from Andreas.
I have a very kind of naive question, which is related to the kind of beginning of your investigation where you said, let's add a magnetic field to the electronic system. Now, you have shown the magnetization as a function of interaction. And my question would be, at zero interaction, you would also see a magnetization. I mean, just Pauli paramagnetism. Now the question would be, how large is the effect as function of interaction compared to Pauli effect in your?
Okay, good. You are talking about orbital magnetization, not CDW order parameter.
Yes.
I discussed two quantities. So you are talking about the last quantity, this one, orbital magnetization.
No, at the very beginning of your talk, you were just as
Which?
Yes,
This one. Oh,
So,
sorry. Here, M is kind of general order parameter.
yes, I understand. But in the example of M being the ordinary magnetization, then I would expect also just a Pauli paramagnetism, which is also at G equals 0. So
Okay. Yeah,
how
for example.
compared to whatever effect is
Okay.
function of G.
For example, in my study, I considered a spinless system. This is just a theoretical toy model, but there are of course spin-free models. And in case of spin-free models, you can have, for example, antiferromagnetic order.
Yes, this is will also be introduced by interactions.
Yeah.
Used by Pauli magnetism. Yes, that's
Yeah. And in that case, in that case, there are several studies and spin Pauli magnetic moment, the effect of Zeeman effect. You mean Zeeman effect? This was also discussed partly. But sorry, I don't remember quite detail. There are some studies, but I don't remember, sorry.
okay. Yeah, no problem. All good.
Yeah, you discuss this case, SU2 symmetry breaking case. In this case, you can have antiferromagnetic order. These are spinful case, and there is some Zeeman effect. Yeah, you are right. In real systems.
Okay. Yeah. Thank you.
Okay, thank you very much. I see no more questions here. So I have also a question. What would be a conjugate field to a CDW, so a charge density wave? Can you?
Physically, for example, potential difference between sites. We have A sites and B sites. you can artificially, at least theoretically, you can introduce potential difference between these two sublattices. This is conjugate field.
Okay. Thank you very much. So if there are no more questions, I will call Pascoal to end our meeting. And I'd like to thank very much to all for their nice talk. And Pascoal, please go ahead, take lead.
Okay, so thank you very much, Aline and Yasuhiro, for the two nice talks. Thank you, Musa, for helping us co-chairing the sections. And before we finish, I'd like to ask the audience two favors. First of all, if all of us can unmute ourselves and give a very nice round of applause to Aline and Yasuhiro. So can you do that, please? Okay, that was very nice. Thank you very much. And now, if you will not mind, I would like to ask you to start your videos so I can have a very nice print of screen of this wonderful audience. Okay, that's perfect. So thank you very much for joining us for this event. So I wish you happy holidays, and I hope to see you next year for the 2021 SCES webinar series. So stay well. It was very nice seeing you all. Bye-bye.
Bye-bye, Pascoal.
Bye. Merry Christmas.
Bye-bye, everyone.